you didn't get the notes, I would complain. I would speak to the administration and say, this guy deserves to go. Leewalk, on a scale of 1 to 10, okay, 1 being like, I'm ready to fall asleep, and 10 being like, I am super excited, I could scream. Where are you right now regarding math? 10? Whoa, he's hiding it pretty well, isn't he? All right, that a boy. All right, way to go. Okay, we want to spend some time today talking about systems. Now, part of the reason why we don't take a more intensive approach to systems is you guys would have seen this in your honors Algebra 2 class. And you would have seen it in your advanced Algebra 1 class as well. So that's why we don't test on it, but we do need to cover the topic as the syllabus says so. So let's spend just a little bit of time doing so. It says graph the following system of inequalities. So we're going to first talk about systems of inequalities. How do I graph that first inequality? Attaboy, start at -1 and go up 2. Okay, so I got -1. I plot that, go up 2 and over 1. Solid line or dashed line? Solid. And do I shade above the line or below the line? Why? But if it read this, I would shade above. So yeah, we gotta consider you gotta consider a little bit about the graph. You guys are absolutely right. We shade down. I just want to be clear. If you were to plug in 0, 0, is 0 less than or equal to -1? Is 0 less than or equal to -1? Yes or no? No. So 0, 0 does not satisfy the inequality, so it is not included on the solution set. So I shade to this side. I draw arrows because I can't really shade with my markers. I look at the next one. Please change the next one instead of 3x minus 2y, change it to 3x plus 2y. This one, I'm going to, instead of putting in slope-intercept form, because that's cumbersome. Do you like to waste time, Jessica? Okay, Jessica loves wasting time, okay? Good. So for those of you who don't like to waste time and you want to save on time, let's graph it using intercepts. If I plug in 0 for x, what's y? 3. Okay. If I cover up y, what's x? 2. Solid line or dashed line? Dashed. In order to determine whether I shade above or below, I'll plug in 0, 0. Is 0 plus 0 greater than 6? No, it's not. So I don't include 0, 0 in the shading, and I shade this direction. And so you can see that I have 4 regions, 1, 2, 3, and 4. Which of the 4 regions ends up being the overlapping region that I should shade? Yep, the third region. And so I know that some of your teachers probably really like to shade lightly, and then shade darker. I'm not a big fan of that. I like to just kind of draw little arrows and then just shade the one that I really want. So, but you do what you want. It's free country. Okay. You try B on your own. See if you can figure out B. Go. Did you come up with no solution? There's no region in which all three overlap. There's no region in which all three overlap. Okay. All right, flip it over. Now, some of you don't like the graphing part. You like the equation solving part. So how do we solve systems? What are our methods? Substitution, elimination. Obviously, we have the graphing. We also have our matrices, which we can use. And we also obviously have our calculators, our graphing technology we can use as well. So you have all those different pieces. And let's focus on the first two. Would you use elimination or substitution in this example? Why would you use substitution, Jackson? You can get that y by itself. 2x minus 4 is equal to y. So what are you going to do with that? Plug that back in 4. Sweet. So 6 times 2x minus 4 is equal to 12x plus 6. Or 12x minus 24 is 12x plus 6. Oh my goodness. I don't know what to do. Negative 24 is 6, so you're telling me no solution. So what does that even mean? They don't intersect. That's what this means. These are two lines. If you were to graph them, they would be parallel. See, if you have two lines, they can either be parallel or they can intersect. If they intersect, they're what we call consistent. They have a point of intersection. They can either intersect once, or if they're parallel, they don't intersect at all. The last option is that if you have one line and the second line actually sits right on top of the first line, then they are what we call dependent lines, and they have an infinite number of solutions. So those are your three scenarios that you could come up with. Would you choose elimination or substitution for letter B? So we would multiply the top through by, very good. Negative 4x plus 10y is equal to 0. Right now, some of you guys are like, wow, I really like this stuff. Yeah, you remember it quite well. And right now, some of you are considering, hey, I could teach 8th grade math. You could. Go get your math endorsement when you go to college and teach elementary, and away you go. All right, add them together. I get 13y's equal to 26. So I have y's too. So which one of these three situations do I have? I have this one, yeah. They don't have to be perpendicular, they just have to cross. So I have a consistent system. I get 2. How do I find x? Plug it back in. So 3 times 2 is 6. Subtract that from 26. So I got x is 5. Now, that's boring. Let's try to get something more interesting. What's different about letter C? Yeah, what does that first graph look like? What does the second graph look like? Yeah, so it's really hard to tell how many times they intersect, isn't it? I mean, maybe they, I don't know. Maybe they intersect like once or twice or 3 times. It's really difficult to tell. So let's allow the algebra to solve for us. We still can use those same pieces. We can use substitution. We can use elimination. Which option is best here? Substitution. Take this, plug it in for y. X cubed minus 4x plus 2 equals negative 3x squared plus 2. What happens to the 2's? They're gone. X cubed plus 3x squared minus 4x equals 0. Now what? You're not a dum-dum. So how many times does it intersect? What are the x values of the intersection? Plug them back in. And it's probably easier to plug in the bottom one. Very good. Will says 2 for the first one. Negative 1 for the second one. And for the third one, negative 4 squared is 16 times negative 3, negative 48 plus 2. Awesome. Now, before we get to the last set of problems, we're going to do this last one here. We get to the last set. And what's different about this one compared to what we just saw? I'm actually going to eliminate the x squareds. I'm going to multiply the top through by a negative 1 and get negative x squared plus y is equal to negative 4. Now, a lot of people question that. They're like, well, can you really do that? Yeah. Elimination is elimination. Doesn't really matter what you're eliminating. It's valid to do it for an x squared or x to the fourth or anything. I cancel those out and I get a negative y is equal to 20. So therefore, y is negative 20. Well, if I have y is negative 20, I got to find the x values, correct? So if I plug negative 20 into the top, I get x squared plus 20 is equal to 4. Yeah. So you get plus or minus 4i. Now, you might be tempted to write 4i and then negative 20 and negative 4i and negative 20. But the fact of the matter is that do those show up on a coordinate plane? No. So do these two parabolas ever intersect? No, there is no solution. However, you guys remember that it wasn't too long ago we took a test on the fundamental theorem of algebra. And the fundamental theorem of algebra said, if it's degree 2, how many solutions does it have? Well, we found 2 solutions. It's just that it never happens on the coordinate plane. So that's kind of an interesting overlap between the two. We flip it over and look at our last piece. Do you remember when you covered systems of 3? Okay, Natalie just invoked the word hate. I usually save that for things like Hitler or oppression or war. Okay, it's all right. She loathes. She loathes the situation. We are going to make systems of 3 easy for Natalie. We're going to make them easy. Okay, so all right. So Natalie, are you ready? Because I need your help. Okay, Natalie, right now you need to pick X, Y, or Z. Okay, great. Pick whatever you want. She picked Z. We're going to roll a Z. Now, Natalie, there's probably better choices here, but I'm going to allow you to make the choice, and we'll roll with it. You can either choose 1 and 2, 1 and 3, or 2 and 3. You need to choose 2 sets. So she wants 1 and 2, so she's going to go x minus y plus z equals 5. And she's going to choose 2x plus y minus 3z equals negative 4. So she chose 1 and 2. She has to choose a second set. She can't choose 1 and 2 again. That would be redundant. She's going to instead choose 1 and 3 or 2 and 3. What would you like? 1 and 3. So she's going x minus y plus z is equal to 5. And 3x plus 2y minus z is equal to 9. That is the only piece that is new about solving systems of 3 compared to what we have just done. As long as you can do that step, solving a system 3 is no big deal. Watch what happens. She committed to getting rid of the z's. So she's going to have to multiply the top through by. So I get 3x minus 3y plus 3z equals 15. I know I've taught this many years, but when I start to go through systems of 3, I reduce my speed by about 50% because I'm much more likely to make a mistake and you're likely to rush. Settle down, get through it. I add. What do you get? Minus 2y equals 11. Good. Because I know if I make a mistake, it's going to take me twice as long to go back and find the issue. All right. Now, I need to get rid of the z's for the next one. Can I just add them together? Good choice, Natalie. I get 4x plus y is equal to 14. The whole reason why we chose 2 and 2 was so that we could get rid of the z and come up with a nice system of 2 that we know how to solve. Did we not just do this on the previous page? Yeah, we sure did. How would you like to solve that? Multiply the bottom by 2. So I have 5x minus 2y equals 11. Again, I'm slowing my pace because I don't want to make a mistake here. 8x plus 2y equals 28. I will add 13x equals 39. X is 3. We good there? Now we got to solve for y. So I need to go back to one of these two. So I'm going to do 4 times 3 is 12. Subtract the 12 over. Y is 2. Now I have to find z. So you're going to go to the very first one. 3 minus 2 plus z equals 5. 3 minus 2 is, subtract the 1, z is 4. So we have the coordinate 3, 2, 4, and I ask you, what the heck does it even mean? If you were to actually graph these 3 lines in a 3-dimensional space, they would have an intersection of what we call this x, y, and z. They would intersect at 3 values for x, 2 values for y, and 4 values for z. So over 3, up 2, and out 4. If you can picture it like that. So over 3, up 2, and out 4 is how we're kind of going about that. And that's the intersection. Tough to draw 3-dimensional on 2-dimensional space. I would love to show you 4th dimensional on a 2-dimensional space sometime. Okay, let's not do letter D and pretend like we did. So I will end with this. You do not need to do this problem right now, but raise your hand if you remember linear programming. Okay. Here's my little plug for